first 2 rockets of the campaign.
We don't want to waste our rocket, because it took us 3 years to make the rocket and only 15 minutes to use it, and I don't want to waste my shot here.
He's using a sounding rocket, which is different from the bigger rockets that carry satellites and humans into space. It's a small suborbital rocket that flies briefly into space, collects real-time data for around 15 minutes, then falls back to Earth. It's affordable, quick to build, and can launch towards a precise point.
The major advantage is that you can launch into a target on the sky.
But there's a limited launch window and only one chance to get the launch right.
We have these unguided rockets. They go where you point them, unless the wind is blowing, because the wind literally just blows them over. We don't launch when there's high wind.
So to measure the winds, they launch balloons with GPS trackers. They're released every 15 to 30 minutes, and then they're monitored to see how fast the winds are carrying them.
The ground winds were 12, 13 meters per second, gusting 17, which is way off.
You're filled with trepidation. Oh my gosh, this thing that I built, is it going to work after all this? So I think we're going to scrub for today. I'd like to thank everyone. I think it was a great performance. Thanks a lot.
This means that we are scrubbing this operation for today and we'll try again tomorrow.
The mission is named Visualizing Ion Outflow via Neutral Atom Sensing 2, or VISIONS 2. In short, they're looking at how oxygen is getting enough energy to escape.
It's a good test of how atmospheric escape works. Earth's gravity should hold onto the oxygen, and yet we see this gas shooting off into space. We're trying to figure out how that works.
That is a science question that has been hanging around for 4 decades.
Fortunately, anyone can see atmospheric escape at the right place and time.
In Svalbard, we have the so-called polar night. It's dark all 24 hours.
This continual darkness is key for witnessing this. This is the cusp aurora. It's a type of northern lights that appears between 8 a.m. and noon, and you can only see it when it's dark during the day. It looks similar to the aurora that occurs at night, but when these iridescent colors dance at this hour each day, 100 tons of oxygen escapes from Earth's atmosphere into space.
This is our sport now to chase the aurora.
Working with them is the iSCAT radar and Kjell Henriksen Observatory. They have additional instruments to find the aurora.
Sometimes it's cloudy, so we use radars to track the cusp.
We can give advice that this is the right type of aurora.
This is the Wall of Science, a collection of data from satellites and ground instruments that helps them predict where the cusp aurora will be.
So the cusp actually isn't a fixed point in space, it kind of moves around.
What's controlling the cusp's movement is the sun interacting with Earth. Our planet is surrounded by a magnetic field that helps us hold on to our atmosphere. But at the north and south poles, the magnetic field bends inwards, creating a corridor between Earth and space.
When energy is released from the sun via a solar flare or coronal mass ejection, all of that energy in the form of radiation rides down the magnetic field lines of the Earth and is transferred and dumped into the Earth's atmosphere.
Electrons cascade into Earth's atmosphere. They accelerate and collide with oxygen particles, giving them energy to release light and sometimes enough energy to escape. Collectively, this forms the cusp aurora and streams of escaping oxygen.
This cusp is in constant motion.
And we've got a fixed trajectory. We really can't aim at where the cusp is. We have to wait for the cusp to come across our line of sight. Can you guys hear Kjellmar? We'd like you, as soon as you see an indication the cusp is moving close, to move it, the radar dish, if we can.
This is iSCAT. It's been very quiet, very difficult to launch.
Do you think we're gonna launch today?
No.
Probably about a 60% chance of launching.
When we started seeing this really good data, this clock started counting down, and that's when everyone realized this is going to happen. We're going to launch.
We're doing everything we can to get that launch off before the aurora goes away. It is really, really challenging and nerve-wracking at that point. You can see the tension just rise. and everybody when that happens.
And so everyone's watching their instruments, getting really excited, and then at T-minus 1 minute, all of us ran out to go see the launch happen. And then we immediately turned around and ran right back in to look at all the data that was coming back from the instruments. You know how much time and effort went into it because we all worked on it, and there's just nothing that compares to that feeling.
Everybody in every one of those little places, really just so happy to contribute to getting this science. It's really an incredible experience.
This is a story about what it takes to launch science instruments into space, but the real adventure will be in the data they sent back. Hidden within the numbers will be answers that reach far beyond Earth, shedding light on how atmospheres throughout the universe change, evolve, and perhaps support life.
Ten, 9, 8, ignition sequence start. Engines on. 5, 4, 3, 2, 1. All engines running. Launch commit.
When you think of NASA, you probably think of space exploration, which is a huge part of what NASA does. But what you might not know is that aeronautics, the science of flight, is also an important piece of NASA's directive. It's even in our name, National Aeronautics and Space Administration. In fact, NASA was conducting flight research long before we put a man on the moon. NASA has flown some of the world's most advanced research technologies, leading to innovations in safety, speed, and efficiency. We here at NASA's Armstrong Flight Research Center have been on the cutting edge of aeronautical development in pursuit of our goal to advance technology and science through flight. Our story began in the 1940s when the National Advisory Committee for Aeronautics, NASA's predecessor agency, teamed up with the U.S. Air Force to fly the X-1 rocket plane in pursuit of one question. Could an aircraft and its pilot fly faster than the speed of sound?
A B-29 will take the XS-1 aloft and launch her at an altitude of about 35,000 feet. The really big moment. Through the sound barrier. The first time ever in level flight.
They successfully answered that question in 1947. New X-planes soon followed, and throughout the 1950s, these aircraft made headlines with ever higher speed and altitude records. The fastest and most remarkable of all the rocket planes, the X-15, was flown from 1959 to 1968. There was simply nothing else like it. Pilots took it to speeds of over 4,500 miles per hour, and some flights reached altitudes so high that they passed briefly into space. Many of NASA's X-15 test pilots actually earned their astronaut wings here. One of the pilots who did not was a young man named Neil Armstrong. However, his experiences flying the X-15, as well as the Lunar Landing Research Vehicle, provided him the skills he needed on later missions, where he, of course, did end up earning his wings.
One small step for man.
Research aircraft like the X-15 provided valuable information about the human body in spaceflight and were critical in the design of future aircraft and spacecraft. The Armstrong Flight Research Center introduced the world to wingless experimental aircraft. Flown in the 1960s and 1970s, these vehicles made a great contribution to the future of spaceflight. In 1977, we applied knowledge gained from the flights of these lifting bodies when we conducted the approach and landing tests, a milestone in the development of the Space Shuttle program. The prototype orbiter Enterprise was used to verify the flying characteristics of the shuttles and to test the systems before they ever went into space. These risky flights, 5 in all, were a success, and the Space Shuttle program would go on to be one of NASA's most important achievements in space travel and exploration. During the life of the program, there were 59 successful shuttle landings here, including those of the Enterprise. Today, wingless lifting bodies are making a comeback as Sierra Nevada brings its Dream Chaser to flight status. Supporting the shuttle program was only one part of our work in the post-Apollo years. Have you ever heard the term fly-by-wire? It describes the use of electronics and computers to control an aircraft. Taking the place of mechanical or hydraulic systems, fly-by-wire technology was first tested on a modified F-8 aircraft in 1972. The flights were dangerous, but they revolutionized aviation. A fly-by-wire production system first appeared on the Air Force's F-16 and is now common on all new commercial airliners, most new business jets, and even in family automobiles as drive-by-wire systems. ABS brakes, cruise control, accelerators, even steer-by-wire are technologies derived from research done at NASA Armstrong, and all are now part of our daily lives. Another example of aeronautical innovation NASA conducted at Armstrong is winglets, which were tested and validated here in the 1970s and 1980s. By reducing aerodynamic drag, winglets improve aircraft fuel efficiency. They are now used on all types of aircraft. We also conducted tests in the mid-70s to find ways to reduce drag on long-haul trucks with aerodynamic fairings, the results of which have also been widely adopted. As far back as the 1960s, NASA Armstrong pioneered the use of a ground control station from which to fly unmanned aerial vehicles, known as UAVs. Becoming increasingly common today, these aircraft are used by the center to develop technology that allows them to see one another and automatically take evasive action to avoid collisions. Known as Automatic Dependent Surveillance Broadcast, or ADS-B, this tracking technology is something that all aircraft operating in U.S. airspace must adopt by January 2020 in order to comply with FAA regulations. Between 2007 and 2009, one of our UAVs, known as Icana, flew over thick smoke and haze to record hotspots and the progression of wildfires in California. Data from the aircraft sensors was downlinked and overlaid on Google Earth maps, then transmitted in near real time to the Interagency Fire Center, where it was made available to fire incident commanders to assist them in allocating their firefighting resources. The effects were dramatic enhancements for the fire crews. Armstrong also operates two early model Global Hawks, another type of UAV. These aircraft can fly long distances, remain airborne for up to 32 hours, and can carry large payloads of instruments into areas, such as hurricanes, that are too dangerous for scientists to fly in. NASA has long been involved in Earth science research, and the Armstrong Flight Research Center operates a variety of aircraft to support this directive, including two ER-2s, a DC-8, and a C-20, as well as the large UAVs. These aircraft are equipped with instruments that researchers use to obtain measurements of environmental phenomena, such as the thickness of ice sheets, precipitation, and air quality. Measurements and readings are often combined with global satellite observations and ground sampling to better understand these environmental conditions. In the 1990s and early 2000s, Armstrong tested hybrid propulsion technology in the hopes of making aviation greener. Other NASA aeronautical research has improved fuel efficiency, lowered noise levels, and reduced harmful emissions. But much more can be done in these areas. That's why NASA implemented the Environmentally Responsible Aviation Project to explore and document the feasibility, benefits, and technical risks that will further reduce the impact of aviation on the environment. The goal is to reduce aircraft fuel consumption, emissions, and noise simultaneously, a much more difficult challenge than working to reduce them individually. As part of this project, NASA Armstrong performed ground tests with its DC-8, measuring emissions and fuel performance of biofuels. Results indicated as much as a 50% reduction in emissions at takeoff thrust, a difference which could significantly improve the air quality around airports. And we are currently working on an adaptive compliant trailing edge flight experiment that will demonstrate a single, non-rigid wing flap that can be flexed in different ways. This leads to more efficient control methods when airborne. Flying from 2007 to 2013 at Armstrong, the X-48 subscale hybrid wing body was another program in NASA's environmentally responsible aviation portfolio. NASA, Boeing Phantom Works, Cranfield Aerospace of the UK, and the Air Force Research Laboratory partnered to study the structural, aerodynamic, and operational advantages of the hybrid model, sometimes called a blended wing body. The concept is a cross between a conventional aircraft and a flying wing. The design has the potential to yield up to 30% better fuel economy than traditional aircraft due to its unique shape. The Stratospheric Observatory for Infrared Astronomy, known as SOFIA, is a partnership between NASA and the German Aerospace Center DLR. The flying observatory consists of a highly modified 747 SP former airliner carrying a 17 metric ton German-built infrared telescope. Missions are flown at altitudes between 39,000 and 45,000 feet, putting the telescope above 99% of the Earth's water vapor. Being able to reposition the telescope anywhere on Earth is a unique capability. Not long ago, for example, it enabled astronomers to chase Pluto's shadow as it moved across the Earth, and SOFIA was able to study the dwarf planet for a much longer period of time than a stationary observatory. The aircraft, flown out of Armstrong's Palmdale hangar, is making infrared astronomy missions available to the international science community. Armstrong Flight Research Center flies modified high-performance aircraft as testbeds for a variety of flight research experiments. In the 90s, we used F-18s to test and demonstrate thrust vectoring, which is a standard feature on today's F-22. We used F-15s for a series of experiments on intelligent flight control systems, a variation of which appears on the F-35. This system makes it possible to recover from what otherwise would be catastrophic failure of equipment, systems, or even portions of the aircraft itself.
Pull up, pull up. Altitude.
Long involved in aviation safety, NASA Armstrong, working with the U.S. Air Force, has been developing automatic collision avoidance technologies for over 20 years. The most recent version of automatic collision avoidance technology, or ACAT, flew on an Air Force F-16D. This integrated hardware and software system is designed to detect and avoid ground collisions.
Flight path marker, please.
In an effort to introduce this development into general aviation, researchers at Armstrong have been using a small UAV, Droid, to demonstrate the ability to implement it using common cell phone technology, which provides for low cost and high accessibility. From its very inception, NASA Armstrong has explored supersonic flight. Today, the goal in this field is to enable supersonic transportation over land. Because planes traveling at supersonic speeds cause sonic booms, which are potentially disruptive to people and structures on the ground, our researchers are working to minimize the boom's impact at ground level. We conduct tests of future supersonic wings and aerodynamic designs, as well as research into the effects of sonic booms on structures and people in pursuit of our goal to one day achieve quiet or low-level sonic booms. Armstrong continues to apply flight research and test techniques to new launch systems, harboring innovative ideas that are now under study and will rapidly be brought to flight. NASA Armstrong also manages the agency's Flight Opportunities Program, created to provide opportunities for space technologies to be demonstrated and validated in relevant environments. In 2011, 7 companies were selected to integrate and fly a variety of technology payloads at reduced costs, a central goal of the program. These payloads, flown on reusable commercial vehicles near the boundary of space, are helping to pave the way for future space exploration. NASA has shifted its approach to space exploration. The agency is partnering with a variety of private companies to develop cost-effective crew and cargo transportation to low Earth orbit, known as LEO. Sierra Nevada Corporation's Dream Chaser space system, which has already done flight testing here at Armstrong, is one example of this. With increased reliance on private industry for LEO transportation, NASA will be able to focus on deep space exploration, taking us into outer space farther than we have ever been before. So, as you can see, there's a lot more to NASA than space exploration. NASA works every day to solve the challenges that still exist in our nation's air transportation system. With green aviation, the agency is helping create safer, cleaner, and more effective travel for everyone through fuel-efficient flight planning and the reduction of aircraft fuel consumption, emissions, and noise. Here at NASA's Armstrong Flight Research Center, we are conducting an unprecedented array of science missions that will seek new knowledge and understanding of Earth, the solar system, and the universe. At Armstrong, we are pioneers, taking the first step in proving new flight technologies, which have practical implications here on our planet, and improve our ability to explore beyond. As far back as the 1960s, NASA Armstrong pioneered the use of a ground control station from which to fly unmanned aerial vehicles, known as UAVs. Becoming increasingly common today, these aircraft are used by the center to develop technology that allows them to see one another and automatically take evasive action to avoid collisions. Known as Automatic Dependent Surveillance Broadcast, or ADS-B, this tracking technology is something that all aircraft operating in U.S. airspace must adopt by January 2020 in order to comply with FAA regulations. Between 2007 and 2009, one of our UAVs, known as Icana, flew over thick smoke and haze to record hotspots and the progression of wildfires in California. Data from the aircraft sensors was downlinked and overlaid on Google Earth maps, then transmitted in near real time to the Interagency Fire Center, where it was made available to fire incident commanders to assist them in allocating their firefighting resources. The effects were dramatic enhancements for the fire crews. Armstrong also operates 2 early model Global Hawks, another type of UAV. These aircraft can fly long distances, remain airborne for up to 32 hours, and can carry large payloads of instruments into areas, such as hurricanes, that are too dangerous for scientists to fly in. NASA has long been involved in Earth science research, and the Armstrong Flight Research Center operates a variety of aircraft to support this directive.
Shutdown sequence, down sequence, down sequence. Shutting down, shutting down, shutting down.
time is a factor. I'm curt with you because time is a factor.
down.